Okay, so I just wanted to make kind of a brief public service announcement. Usually people are not surprised the day that they come to class and there's a midterm. But just in case you're one of those people that might be surprised, so on Thursday next week, no, Tuesday next week, just Tuesday, right? There's going to be a midterm here in this room for this class, okay? Astoundingly, we're halfway through the semester, almost up to like midterm grades and stuff. So what I'm going to do on Thursday is I'm going to have probably a somewhat shorter lecture. I'm going to review some of the kind of, high points of the class so far. We've put up some sample questions, like midterms from previous years. So there are some sample questions that are up on the website for the midterm review lecture. We might put a few more up before the midterm. I should sort of also mention, so this says last assignment due, and that doesn't mean it's the last assignment. It means it's just the most recent assignment. So that's the SGD assignment, right? There are going to be assignments right after the midterms, so we'll go back to that kind of thing. So there's not going to be any new material on Thursday. Next Tuesday, you will be responsible for everything we've covered so far, including today's lecture. Okay, so it'll be kind of fair game everything over the first half of the class. Okay, so here's some kind of like teasers for the midterm. So like I said, there's some sample questions that are up. The syllabus is a little different every year, but the first half is mostly the same. So there may be some questions like on phrase finding that used to be an assignment, and now it's just something I sort of barely covered quickly. So use your judgment if there are things that we didn't cover as much. If you've been doing the quizzes along the way, then don't think it's like, oh, well, the quizzes are real easy. The exam should be just a snap. So one thing is the exam we grade by hand, so we don't have to just make a multiple choice, true, false questions. So the quizzes are really just to kind of make sure you're staying up with the lectures and don't fall behind. And so I kind of keep people engaged. It's good to kind of go back and actually review something and think about it after someone's taught you. There's a lot of evidence that shows it's actually better to sort of sit down and think about things later. So the quizzes are a way of forcing you to do that. But the problems aren't going to be quite as easy as the quiz problems. There tend to be problems that rely on the homework. Most people have done the first set of assignments. If there is a homework that you had to drop, you're like traveling for interviews or whatever, then make sure you understand that homework. Look at the TA's sheets, look at the questions, make sure you sort of understand what those things are with the thought that, well, someone might come up with a question related to that homework. So you can't bring the textbook because there is no textbook for this course, okay? You can't use the internet either, but just so you don't have to like sort of memorize all this arcane terminology I've been spouting for the last few weeks, you can bring in a sheet of paper with notes, okay? So no poster board, okay? Just like one 8.5 by 11 sheet of paper. You can use front and back. You can make the font as small as you can read without external assistance, okay? You cannot bring in like an electron microscope or anything like that. If anything magnifies much more than these guys, then I'm going to take it away. All right. So that's the story for the midterm. Any questions? Does anyone in this room have a conflict with the midterm or the final, or feel they have a conflict? All right. One person has like sort of made sort of an appeal for mercy because they have 3 midterms in one day, or maybe 2 days. All right. Okay. Let me quickly do a wrap up of what I was talking about the last session before we move on. So we made this long detour into just perceptrons, and then I presented this really pretty paper about distributed training strategies for the structured perceptron. Okay, so the key idea in this paper was this technique called iterative parameter mixing, right? So here we basically shard the data, so we split this data into different pieces. We run a little bit of learning on each shard of the data, then we take the parameters that we've learned, the weight vectors that we've learned, and we average them out, okay? So we combine the weight vectors, and we take those weight vectors and we redistribute it to all the different machines, okay? So that's what iterative parameter mixing is. This was the particular case of doing it for perceptrons. There was some nice analysis. So we know exactly how to do this part here with the blue arrows, okay? This is just basically, you know, running a map process, essentially, right? We're just running a sequential process over a shard of the data. Nothing complicated there, all right? And we sort of know how to do these things. So this is kind of like a reduce step. And then we have to take all the results of the reduce and we have to broadcast it to every worker. So it's a combination of two things. And we've done these things in the past. You know, in our assignments, we looked at broadcasting counts. You know, putting them in the distributed cache so that every worker can access them. And of course, we've looked at how to do reduce type operations, okay? But this is sort of actually a special case because there are these two things happening in sequence, and it's happening over and over again. So there actually are some tricks for doing this particular, you know, basically aggregate and then distribute operation. And I mentioned this very briefly. So in the algorithm, you basically, the parameter mixing algorithm is that you basically run the perceptron for one pass, then you do this averaging, and then you sort of distribute it to everybody, okay? So this is my text version of this. So, and I said briefly, it's like, well, we can use an operation called all reduce. So I'm going to spend the next 5 minutes maybe talking about all reduce. It's not very complicated. So this is, I'm mentioning this because it's actually a pretty common pattern, this iterative parameter mixing algorithm. And using all reduce is sort of a common trick, okay? So the name actually came from the message passing interface, not from Hadoop. There are some Hadoop implementations of it. The Vopal Wabbit code that you guys are busily basically approximating right now, John Langford's code has got an implementation that's pretty general. So let me explain what it does. So we've got a bunch of workers, and they each have values. All right, so here these values are just scalars, 1, 2, 3, 4, 5, 6, 7, okay? And what I want to do is I want to reduce these things. My reduce operation is going to be sum, just to be simple, and then distribute them to everybody, okay? So what I want at the end of the day is everybody knows what the sum of the whole set of workers is, okay? The actual algorithm, it's an average, not a sum, but this is close enough, okay? So how do you do this? Well, you could choose some central point. Okay, we could basically do a reduce operation. We could pull in the result of that sum, and then we could copy it out to every place in the every worker in the file system. Okay, and that's sort of the obvious way of doing it. And the obvious problem with that is it puts one node in the middle. So one node is getting n inputs and outputting n things, all right? So a better architecture for kind of minimizing communication might be something like this. So we'll take the nodes and we'll put them in a binary tree, okay? Well, I don't know, binary tree, we'll put them in a tree, okay? And then when I want to do the sum, what I'll basically do is every node will send its value up to its parent, okay? So these guys will send, let's back up, these guys will send their values to the parent, and the parent will do the local summation, right? So we'll end up with this value. Then those guys will send their value to their parent. Okay, and finally, this will sort of terminate when somebody is at the root of the tree. Okay, now we've got the sum over everything in the tree, and we can basically broadcast it back down. So each node is only getting input from 2 other nodes. It's sending output to 1 other node. And then later on, it's going to get an input from its parent, 1 node, and send output to 2 nodes. So there's not a lot. We're sort of minimizing the amount of communication. There's not one node that's sort of in the center of the star. Okay. So it's basically a reduce combined with a broadcast step. So there's a very simple idea. So doing this in a Hadoop setting is kind of messy. So what John Langford's implementation does is it basically works in a couple of different stages. So first you set up a spanning tree server. So this is something that's not written in Hadoop. It goes out, finds all the worker processes, and links them up in a binary tree. Okay. Then you create something which is kind of like a fake mapper. It gets a sequence of data, and it's actually going to cycle through it as many times as it needs to do. All right. There's not actually going to be a reduce step. Instead, what's going to happen is that process is going to run for a while. Let's say make one pass over the data. And then it's going to call the all reduce method. And when the all reduce happens, then it starts communicating with this spanning tree server. Okay? And it's going to keep communicating until the all reduce operation is finished. So when all reduce gets called, then all the workers are basically going to wait for that same all reduce to happen. So they'll all synchronize, just the way mappers synchronize when you do the reduce step afterwards. Okay? So whenever there's an all reduce, basically you'd synchronize. So the loop you'd write is basically go through the data, call all reduce, go through the data again, call all reduce until you decide you're finished. Okay. So that's basically the main idea. There are a couple more slides here about how to deal with the possibility of failure, which I'll maybe skip over. You guys can read through this if you are really interested. But let me just kind of jump ahead and look at some numbers here. So this is the speed up, okay, for getting a fixed error on a big learning problem, okay. So the baseline is running with 10 nodes, and he basically goes up to another factor of 10. Okay, so with 10 times as many nodes, you basically get about 6 times faster, which isn't bad, because there's more communication going on the more nodes you have. Okay. So this is something that's sort of reasonably successful. Here's another nice set of measurements. So this is another big data set. I think it's 50 million examples, and each example is pretty long. Okay, so each example has 3,300 non-zeros. Okay, it used to take 3 days doing SVM, and now we're using Vopal Wabbit with this approach. Okay, so it's about an hour with 100 processors, and it goes down to 800 seconds with 1,000 processors. So again, we're getting like sort of a pretty good speed up, even going to this very large cluster size. Okay, and you can also sort of break down what's happening. So when you synchronize, you got to wait for the slowest guy to finish. Okay, so one thing which matters is what's the maximum time it takes for a worker to finish its little scan through the data. Okay, so if you have 1/10 the data, you'd hope that you would take 1/10 the time, right? But there's also some variance in the individual machines and the individual data sets. So the actual max doesn't grow as fast as the number of machines grows. Okay, so you'd hope that would be like 46, but actually the maximum time is 95. So that's what you're waiting for between when you synchronize. So part of the reason you don't get perfect speed up is because if you've got 1,000 jobs, there's more of a chance that one of them will sort of lag behind and be slow. And you've got to sort of allow for that. The other thing they look at is the communication time. Okay, this is the number I think we kind of really care about. So this is the median communication time. All right. So that's the time it takes to send these signals around, on average, discounting sort of like kind of outliers. Okay. So since many of the communication steps can be done in parallel, right, it's only ones at the very top of the tree that are sort of like blocking things. You're less likely to see blocks because of communication. So the median communication time is also getting smaller, okay? Because you're passing around weight vectors which are computed over a smaller subset of the data. So that's something that's good. But at the end of the day, you're sort of seeing the communication time, the time it takes to synchronize the parameters, is getting close to the time that it takes to actually pass through the data, or not on average, but for the worst case, right? So probably if you went from 1,000 to 10,000, you'd sort of stop seeing improvements. So that's kind of the short story. So now you know roughly what all reduce is. Question?
Is that the only reason why, like as you scale the number of nodes or reducers, it doesn't, like the walk-up time doesn't drop linearly?
So there are two big reasons. One is the variance between the workers, okay? So whenever you have to synchronize, as you get more workers, the variance starts to kind of dominate. So essentially what happens is you're waiting for the last mapper to finish or the last reducer to finish, okay? So that's one thing that happens, all right? One is the variance. And as the set of workers grows, the variance is also going to grow, okay? The other thing that happens is you end up doing more total communication, okay? So since you're sending information to, 1,000 different machines, we're trying to do it as efficiently as we can, but, just like sort of concretely, right, the number of passes we have to go to propagate information up that tree, it's log n, right? So you're going to spend more time communicating as you get larger and larger sets of workers as well, even with all reduce, okay? So that's another thing that happens, okay? Those are kind of like the two major things. Does that help? Okay. All right. All right, so now we're going to switch gears. We're going to talk about a different problem with a very similar kind of solution, okay? So we're going to talk about matrix factorization, okay? So what's matrix factorization? So we have a matrix, and I basically want to decompose this into the product of two matrices, okay? So we got one tall, skinny matrix and one kind of low fat, wide fat matrix. So together, these don't have nearly as many numbers as this one big matrix, okay? But if we choose these numbers carefully, we might be able to approximate this when we multiply them out, when we look at the outer product, okay? So K here is going to be the width of our skinny matrix, or the height of our flat one, right? So by choosing K, we're basically choosing sort of a smaller set of parameters. So we're doing more compression. So when would you want to do this? It seems like a very abstract problem, which is sort of good and bad. It's good because we can use it for lots of things. It's bad because it's kind of hard to get a handle on. So one task it's often used for is collaborative filtering. How many people have used a collaborative filtering system? Okay, some people have used it. I think most of you have used it, and some of you don't know that you've used it. What this is basically any system that's sort of making you recommendations by looking at what other customers do, right? So when you go to Amazon and it's got like a list of like, recommendations for me, right? That's based on collaborative filtering, all right? If I go to Amazon, it's going to pick things that it thinks I'm going to like, which in this case is actually really stupid because this is just something I already bought. And how many headbands do you want? But so this is collaborative filtering, and it's used in a lot of different settings. The Netflix prize was one example of collaborative filtering. So that was basically doing collaborative filtering, social recommendation for movies, all right? And the idea is you sort of take everybody's Netflix cues and use that to recommend what other people, what you should be watching on Netflix. And this was a big thing when it came out. It was $1 million grand prize, a really huge data set for the time. Okay. So how does this turn into collaborative filtering? Well, we've got this idea of approximating one big matrix by the product of two smaller matrices, right? So the big matrix we're going to approximate here is basically rating information, okay? So basically, each user here corresponds to a row, and each column corresponds to a movie. And the number we put in here is like a number between 1 and 5. And it's what the user would rate the movie as, okay? So some of these things, users have actually gone in and rated movies, and they said, oh, I thought that was a 5, or this was a 1, or this was a 3. So there is some things that are actually known. And there are some, of course, you don't know, right? So this is a matrix where we have some unknown values, which, in the paper I'm going to talk about in a minute, are just approximated by putting zeros in that matrix. So you have a big sparse matrix. All right? So these things that you multiply, you can also view. So obviously, the number of rows for this thing is the number of rows here. So each row here corresponds to a user. And likewise, each column here corresponds to a movie. All right? And what you're basically doing is you're approximating the rating as the inner product of these numbers and these numbers. Okay? So if you like this pair of numbers, this set of numbers for each user can be thought of as some sort of, kind of latent, hidden representation that that user has. And the same thing for the movies. Okay? So here I let k equals 2, so everything's in two-dimensional space. So here's a picture from this. Okay? So the squares are the movies, and then these like cartoon guys are people. So we put things in 2 dimensions. All right? So we basically assign 2 numbers to everybody when we factor the matrix. 2 numbers for every user, 2 numbers for every movie, so they're all in 2-dimensional space. All right? And the idea is the rating will be the product of its position in of the user and the movie's position. So when you have 2 things that are pretty close together, that basically would sort of indicate sort of a large number, right? And when you have 2 things that are far apart, you indicate a small number. So we've kind of labeled these dimensions as like serious versus not serious, and guy movies versus girl movies. All right, just so they kind of make sense. So so here's the color purple, kind of serious girl movie, and then here in the other corner we've got Dumb and Dumber, or I guess Braveheart in this corner, kind of a serious guy movie, and so on. All right. So this is a visual picture of what we're doing here for the particular, case of 2 dimensions, which we can draw on a screen. Here's another example. All right, so matrix factorization doesn't have to be about ratings. Here's some data. So this is an example from Bishop's textbook. What we do is we take a particular image, and what he did is he took that image and he slid it around in a square. So we translated it a little bit and possibly rotated it a little bit. So you have many, many copies or noisy copies of the same image. So that's the data. And what we do is we use matrix factorization. So in matrix factorization, what you're basically doing is you have essentially what you're building is a prototype of each of these images. Okay? So one prototype might be just the average of these things. Okay? So this is another prototype. So the blue basically means it's positive and the green means it's negative. So if I take this guy and I add it to this one, then I'm sort of adding a little bit more blue over here, and then I'm kind of subtracting some blue where this green stuff is. So it would look a little bit like that version of that 3 tilted a little bit. All right. So this little prototype here is basically sort of another, basically if you add it to the mean, then you'll sort of get a slightly tilted 3. And this is one where it sort of gets a slightly shifted 3. All right, and you get a whole bunch of other variations of this. So now if I take a particular picture and I want to approximate this, okay, then there's a whole bunch of approximations I could imagine using, but we're going to look at approximations that are just sums, weighted sums of these prototypes. Okay, so the simple one is to just use the average. Okay, so that does approximate this, although not very well. All right, if I take 10 prototypes and I sum them up, in just the right way to give that reconstructed image, I get something which looks pretty close. All right, if I have 250 prototypes, and this is like 10,000 images, I guess, then I get something that looks very, very similar to the original image. Okay, so in pictures, what happens here is I've got prototypes, so maybe this prototype here. So I've got 1,000 images. Okay, each image is maybe like 100 by 100 pixels. Okay, so each image is so each one is 100 by 100 pixels, so it's 10,000 pixels. So this matrix that I'm approximating here is basically there's one row for every image. So I'm taking the pixels in this image and just sort of stretching them out to one long vector. Okay, so what we're trying to do is we're trying to predict the rows which are reconstructed images, and each one of these things is going to be a particular way of weighting the prototype. So each row here is a prototype. So it gives you a value for each of these 10,000 pixels, right? So one of them is this average, another one might be this guy, right? Okay. So let's say we have these just 2 prototypes here. And then each one of these things are basically say how to weight those 2 prototypes. So this is, the mean, plus we figure out how much we're going to shift it, right? This one's the mean, maybe we shift it, the other direction or something. Okay. So this is how we would reconstruct those images, all right? So this would be a reconstructed image in a row in this matrix. This is a prototype image, and this is, for every image in the data set, this is our specific way of choosing weights for the prototypes that reconstruct that image, all right? So this is another example of matrix factorization, okay? So these are called PC1 and PC2 because I use this slide. We're talking about a particular matrix factorization technique called principal components. Here's another example of matrix factorization. All right, so what I'm going to do is I'm going to model a corpus of documents. All right, so this is this nice example I got off the internet. All right, so this is the corpus. All right, that's the whole corpus, not examples, that's the whole corpus. Okay, so the matrix I want to approximate here is basically this matrix. So each column here is a document, and each row is a word. Okay, so it tells you what word appears in which document. So it's just a matrix, just a document term matrix. Okay, so each row here corresponds to the inverted index for a word. Okay. So what I've got here is I've got the documents on this column, and I've got the terms here. So what instead of having, so to reconstruct it, what I do is I have a set of terms that tend to co-occur together. So I sort of have a cluster of semantically meaningful terms. All right, so each one of these rows is a cluster of terms. And when I want to reconstruct a document, I basically sort of say, well, how many of these things do I want to mix in, and how many of these things do I want to mix in? And that gives me a row, which is an approximation of the counts for the terms in that document. All right. So again, just to sort of like make it concrete, here are some of the things that they came up with. And here's looking at it sort of in 2 dimensions. All right. So these boxes are the words, okay, and these circles, these blue circles, are the documents, the titles. All right. So roughly, there are some things that kind of cluster. There are a couple of things here that sort of seem to be about real estate. And one of these is the title, Investing for Real Estate. The other one is ABCs of Real Estate Investment. Okay. And then this one is like common sense investing, and this is guide to stock market investing, and so on. All right. So once again, we have objects. We have the features of those objects sort of in the same space, right? And similarity, inner product in that space is going to be used to predict how each object interacts with all those features. Okay. So these are 3 examples of matrix factorization. So another thing that matrix factorization is closely related to is clustering. Okay. So how many people here have studied k-means? K-means clustering algorithm. Okay. So in k-means, what you do is you have a bunch of examples, and you have a bunch of clusters. Okay. So if you're doing k-means for documents, each cluster will correspond to a weighted set of examples. So each cluster basically is a set of terms. Okay. So it's a weighted set of terms. So each one of these rows in this set here would basically be the kind of correspond to a centroid of a cluster. Then every document is assigned to a single cluster. So this is maybe a special case of the more general thing where each document is a weighted sum of clusters. Okay, so here it is a weighted sum, but everything's 0 except for one thing, which is 1, right? So if you use this basically says this is cluster 2, that's cluster 1, and so on and so forth, right? Then, if you do this multiplication, then what you'll get out is for every document in your case, what you'll end up with is the means of the cluster that it's been assigned to. All right. So that's also an approximation to the original matrix, right? So you're approximating the original matrix by a product of these two things. This one is very constrained, right? It's a binary matrix, and there's only one, one in every row. All right. But it's also basically analogous to matrix factorization, or you can express it as a matrix factorization. So another way of thinking about matrix factorization is it's kind of a soft version of a k-meansy sort of clustering. So there's no constraint that the clusters or the cluster centers, the things that we use, our prototypes, there's no constraint that those are basically just averages of examples. They can be anything you want, all right? And there's no constraint that we're assigning something to a single cluster. Instead, we're basically sort of trying to approximate something by taking for each object, constructing for each object a weighted sum of the prototypes. All right, so this is matrix factorization. Are there any questions so far? All right, so the next question is, how do you do this? Okay, so the task we're looking at here is that someone gives us this matrix, all right? We know some of these values, and there are some other ones we don't know that we'll just represent as zeros. Let's say they also tell me how wide I want this matrix to be. So they tell me sort of the number of prototypes I'm going to use, all right? And now I want to come up with prototypes, and I want to come up with a reconstruction of each example as a weighted sum of prototypes that approximates this data. So I'm given this, and I have to find these, okay? So that's the learning problem, all right? So I'm now kind of switch from this kind of general description of the problem to a particular paper. So these guys had a beautiful talk on this work a few years back, so I'm really following their presentation pretty closely. They start out just like I did by kind of reviewing what collaborative filtering is. So they have these examples. They're 3 users, and they're 3 movies. And they're, I guess, therefore 9 ratings, and 3 of them are missing, and the other ones are here, right? So we've got 6 that are there and 3 that are missing, all right? So they're really going to do experiments on the Netflix data, which is slightly larger. But our goal is to basically approximate this matrix, all right? And we're going to do it this way, all right? So their notation, R is the number of prototypes that you have, okay? This matrix is called W, I think for limited width. This one is called H for limited height, okay? And this one is called V, all right? So we're learning W and H, we're given V and R, all right? So if we're in 2 dimensions, we basically have to figure out where to put all these positions, all right, in such a way that the inner product approximates the ratings best, okay? So what we might do is something like this. What we might do, so here, let's see, what is this doing here? I'm trying to remember. So here we have these actual numbers. These are the actual ratings we've gotten, okay? What we want to do is we want to match these as closely as we can, just using inner products over some small matrices. Okay, so we're actually going to do this with not even dimension 2, we'll do it with dimension 1. So each one of these guys gets one number and it just sort of gets multiplied, right? Okay, so we're just going to basically sort of approximate these things by a multiplication of 2 different numbers. Okay, so this is our approximation, all right? And you can sort of see it's pretty close most of the time, okay? And what we really want to do is we want to see, well, can we now guess whether Charlie's going to like the matrix or not, right? Well, we can guess. We can predict the rating. We can sort of plug in. We can just multiply these guys, and we'll get a number, okay? And the question is that sort of a good prediction or not? So to get this, what we need to do is what we're going to do is turn this into an optimization problem, okay? So the simplest thing we can imagine doing is the following. We're going to minimize the loss, right? So we have some non-zero values that we know, all right? They're these black ones. So we're going to sum up over all of these. We're going to sum up the square difference between what we predict and what the actual value is, Okay, we're not going to be able to get to 0 because we sort of don't have enough parameters, right? We only got 6 parameters here, and there are 9 numbers to estimate. Okay, but we should, be able to approximate that. So we're going to find the W and H that minimize this loss. So this is just squared error. Okay. So for actual collaborative filtering tasks, you often want to do something a little bit more complicated. What you might want to do is, in addition to basically looking at an inner product of a user vector and a movie vector, you might want to have some intercept terms, basically. It might be that some users always give high ratings to everything. So essentially, you should sort of add a number, right, for that user just to put their ratings in the right scale. So somebody basically rates everything between 3 and 5, right? So maybe you want to just basically add an offset. And it could be the same thing for a movie, right? So Dumb and Dumber, maybe everybody hates, so you might want to give it sort of like a negative offset. Casablanca, everybody loved it, so maybe you want to give it a positive offset. So we can also learn these vectors, which are kind of user terms that are specific to a user but independent of a movie, and likewise, things that are specific to a movie and independent to a user. You might want to add another, like a global offset term, right? And that will give you this optimization problem. So now we're trying to minimize W over WH and also these other vectors, all right? You might want to add some regularization, like we do in logistic regression, to keep the parameter values from getting huge. That might give you better generalization. This would be a more realistic loss function, all right? But what I'm going to describe is actually something you can do for a lot of different loss functions, all right? So the main assumption I want to make is that the loss can be written this way, all right? So the loss is some function of W and H and V, okay? And it's the sum of losses at each cell in the matrix that you know the value of. So Z is the known values, the non-zeros, okay? So this broader thing doesn't satisfy that because there's this U and M, right? This simple loss function does. We could extend it a little bit to deal with these U's and M's, but let's kind of go back to the simple loss function here as we're kind of thinking about this. So we're assuming that the loss function decomposes this way, okay, which is true for squared error and some other ones, all right? What we're going to do is we're going to do stochastic gradient descent, all right? And what we're going to do is, well, what does it mean to do stochastic gradient descent here, all right? So normally you basically sweep over the examples in some random order, okay? Here what I'm going to do is I'm going to sweep over the known values in the matrix V in a random order. So what I'm going to do is I'm going to cycle. I'm going to pick a known value, so of an ij at random. Okay, so essentially I've shuffled all the points in that matrix V. All right, and I'll compute the gradient. So before we were looking at the gradient of the weight vectors for a classifier. Now they're basically two weight vectors essentially to consider, right? There are two things we're learning, W and H, right? We have to learn both of those, right? So what we want to do is we want to compute the gradient of W and also the gradient of H, all right? So their algorithm is the following. What we're really going to do is we're going to compute the gradient of row I and the gradient of column row I of W and column J of H, all right? So the step is the following. We're going to basically go through and figure out what is the gradient of that row. All right, so what's the gradient of the loss function with respect to that row? We'll take a step in that direction, okay? And we'll use that to update W, all right? But we're not going to replace W just yet because I also need to compute the gradient for H. So I need the old value of W for doing that, right? So for the gradient of H, I'll do the same kind of update using the gradient of H with respect to this loss function, okay? Then finally, I update W with the new value. Okay, so epsilon here is basically our learning rate. Okay, and don't worry about epsilon times n is the learning rate. Let's say. Okay, and this is basically, so we're allowed to do this because the loss function decomposes this way. So this loss function only depends on V, the ith row of W, and the jth column of H. All right? Right? So those are the only things I need to worry about when I'm doing the update. Okay. So why does this work? Let's kind of take a picture of this. So we've chosen a random ij, all right? And what I'm updating is this row and this column, okay? So this is the specific column of the prototypes that relates to this part of the prediction matrix, of our ratings matrix. This is the row of the user. So this is a particular attribute of the movie that we're using here. This is a particular movie we're using. This is the particular user that we're talking about, right? Okay. So if we look at what's going on, so this number here is an inner product of this row and this column, right? So the gradient of Wi with respect to this is going to be 0 for all the other W's, all the ones that aren't in yellow here, right? And similarly, the gradient of H with respect to these is also going to be 0. So a gradient of 0 basically means if I change one of these other values, it's not going to change this the loss at Vij at all, right? It's not going to change the prediction at Vij, so therefore it's not going to change the loss at Vij. All right. So the assumption we're making here is that the loss just depends on these guys. All right. Again, just to kind of like step through this and verify it, we're saying that the loss with respect to Wi for W and H, okay? All right. So since this can be written as this sum, right? Well, this is just writing down what the loss function is, okay? And then the claim here is that the parts of this loss that are in the summation that go to 0, that are outside of the set for I, that are different, where I prime is different from I, will all be 0, okay? So that follows from the assumption about the loss function, and similarly for H. Okay, so this is kind of a common sense result. You know, we're basically saying that the loss depends on this prediction. The prediction only depends on this row and this column. So those are the only things they really need to worry about updating. All right. So I kind of find it a little bit helpful to think about this SGD and kind of compare it with the SGD for logistic regression. So for logistic regression, you can imagine, let's say, each of the elements of W is an example, and it has a fixed representation. So each example is a vector in some fixed representation space. And then you're learning weights for that example, all right? So essentially, you're learning a weighted combination of those features. If you had one class, then you'd be approximating a matrix that just has one column. If you had multiple classes, you'd be maybe approximating multiple matrices. So what's kind of going on here? If we're looking at linear regression, then the loss really is just the dot product, or the difference between the dot product and the value squared. All right. So the loss function just depends on that example on the weight vector. Okay. So here this is kind of similar, except there are two things we're updating. We're updating we're updating both W and H. Okay, so if we were doing, let's say, logistic regression, you've got some target value Y, and you've got some product of W and X. Okay, so let's say X here is the example, maybe the movie, and W are the weights. All right. Okay. Let me back up. Let's think about the problem like this. So what I'm going to do is I'm going to learn, the way I'm going to approximate my movie matrix is I'm just going to do linear regression for each user. So for every user, I'm going to have a set of linear regression coefficients. Okay, I've got some way of representing movies, and we're going to basically just take those, take the dot product of those things and use them to predict the weight. So I'm treating this as basically a whole bunch of linear regression problems. All right. So each one of these, we've got a set of weights for that particular user, and we've got an example, a set of features that correspond to the movie. All right. So normally in linear regression, we would just do an update where we update the user weights. Okay. So the weights of the classifier. Here I'm actually updating two things, right? So I'm going to update these weights W, and I'm also going to update the weights X. So we're kind of simultaneously learning the user-specific classifier and the movie representation. Okay, so let's talk a little bit about what other loss functions you can plug in here. So the real constraint I have basically is that the loss function only depends on the row and column being considered. Okay. So they have a couple of different loss functions. This is the simplest one to think about. Another one that's common is the same thing with some sort of regularization, and that works. This is another one that they look at where you essentially add sort of an extra diagonal term to W and to H. Okay, so you can kind of think of this as like, an IDF factor. So if you were looking at document completion, you might start with some initial weighting of the terms, and then you might say, well, let's try and learn that. So this would be another slightly more complicated loss function. If N1 and N2 are fixed, then this is, again, just sort of learning W and H. This is sort of a probabilistic one that some people have talked about, which has kind of a complicated optimization scheme. But the gradients of these things work pretty simple. So the non-zero loss function is just this. Okay, so the loss, since we're just looking at the squared error here, it's basically the difference between Vij, the target value, right, and the predicted value. So WH is the matrix of predicted value. So it's that difference times H kj, and this one it's that difference times WIK. All right. So the loss functions are actually pretty easy to write down. If you add these regularizers, again, it doesn't change very much. We're just basically adding another kind of decay term, which depends on the value of W and H. So this is again, very similar to the case for logistic regression. So this is the basic idea. So let's sort of see how this works. So the short story is this actually works surprisingly well. So LBFGS is a second order method that is a kind of very general optimization method. It's been used for a lot of linear classification type tasks, but it doesn't work very well for this one. Alternating least squares is a method that's specifically designed for matrix factorization, and this is their SGD. So if you're basically looking at minimizing the loss, and this is squared loss, then this does pretty well. It minimizes the loss very quickly per epoch. Okay, so this is the basic idea. Okay, so this is taking gradient descent and moving it from learning a classifier to learning to approximate a matrix, all right, to do matrix factorization, all right. So this was not actually the big idea in their paper, okay. So the big idea in their paper was how to do this and parallelize it, okay. So stochastic gradient descent is a great algorithm. It's very efficient. You can do it in a streaming sort of way. It's really well suited to big data sets, okay. But it's even nicer if you can take that and parallelize it. So let's take a look at what happens when you try to parallelize it, okay? So they start out by talking about a couple of baselines, and these are the same baselines McDonald uses, okay? So one of them is you basically just shard the data, run SGD on different subsets of the data, so run your optimizer separately, and then average the results, okay? So before we had these three nice convergent lines for these different algorithms. So this is what happens with the parameter mixing. So we just run things independently and average. It's absolutely terrible, okay? This is actually way worse than you'd see for a problem like, let's say, classification. So why is that? The problem is that matrix factorization is not convex, right? So in particular, right, you can sort of see it's not convex because you could take those prototypes and you could construct another solution by just taking the prototypes and rotating them, right? So you could just permute the prototypes and then permute the weights of the examples. It has the same loss, all right? But it's a really different solution. It's in a different corner of the space. So those are two different local minima, right, of the loss function. And there's nothing in this algorithm, this parameter mixing algorithm, that deals with that at all, okay? We could start off, and one could sort of take you to like sort of saying that the first prototype is, the average, and the next one is, rotating the image, and another one could sort of switch them exactly, rotate them in a different way, and then when you average them together, you'll just get garbage, right? So the prototypes might even sort of have the same meaning in different runs, all right? So not too surprisingly, no matter how much you run it, it doesn't really, no matter how many epochs you run, this doesn't really help, okay? So that turns out to be a really bad algorithm for non-convex things. So the next thing to do is to try McDonald's algorithm of iterative parameter mixing, all right? So here, what we basically do is we run SGD on independent data, then we average the results, and then we repeat, distributing the average results and running again, all right? So this is this iterative mixing algorithm. So this is just basically sharding the data and then being oblivious. This is sharding the data and resynchronizing the data after every epoch. And it is converging, okay? It's not converging super fast, though, all right? So, so this is a case where this fancier algorithm, iterative parameter mixing, doesn't seem to work great. So these guys came up with a rather clever idea. All right, so the problem with parallelizing SGD is basically when you do SGD on example 1, it updates the parameters. So then the next example you use is going to have different parameter values, so it'll have a different result. So the order of updates makes a big difference. So when you parallelize things, you could get a very different result. All right. So their observation here is that for matrix factorization, it's not true that all the steps are dependent. Okay. So here's an example. So let's pick this pair here and this pair here. Okay. When I update this one, I'm only going to update this yellow row and this yellow column. All right. When I update this one, I'm only going to update the green row and the green column. All right. Those things don't overlap. Okay. So the parameters that we update here, these yellow things, are completely disjoint from these green parameters that I update here. All right. That means I could do Zn and Zn plus 1 in either order, and I'd get exactly the same result, guaranteed. Or if you want to do it another way, I could take Zn and run it on one machine and Zn plus 1 and do it on a second independent non-communicating worker machine, all right? And then, sum the results at the end, and again, I would get exactly the same result, all right? So if I can figure out which of these steps are not dependent, all right, that are orthogonal this way, they touch different parameters, then maybe I can do something clever to parallelize things, all right? So it's not the case that any pair is like this. So this guy, this yellow guy and this pink guy, these share these pink parameters in the column space here, all right? So when I update this one, those column values are going to change. When I update this one, these column values are going to change. So the result of doing this is going to depend on this result, okay? And similarly, these guys are in the same row. It's also going to obviously have dependence for the same reason. So these are dependent steps and these are independent steps. So what we're basically going to do is we're going to like formalize this. So we're going to basically say two elements, two ij pairs in this matrix are interchangeable if they just have different rows and columns. So they're updating different parameters. So when they're interchangeable, the SGD steps become parallelizable. That's the kind of key idea, right? So now that suggests an algorithm where what I do is instead of randomly sharding the data, what I'm going to do is I'm going to shard things so I get as much independence as possible, right? So here's their idea. Okay, I'm going to take this data, all right, and I'm going to put it in blocks, all right? So I'm going to take some sequence subset of the rows, maybe we've broken into 3 subsets here and 3 subsets there, okay? And now I'm going to basically use that to divide the whole space into blocks, all right? So I'm going to pick a diagonal, all right? So I know that these guys don't depend on these guys, right? Or the parameters for these guys are disjoint from the parameters for these guys. And those parameters are all disjoint from these parameters, okay? So what I can do is I can do SGD on these blocks in parallel, okay? So the basic idea is that idea, okay? So what we're going to do is we're going to pick a diagonal, and then we're going to parallelize. So we're going to like do each of these blocks in parallel. And then we're going to, actually I don't have a picture of this. We're going to take this and shift the diagonal over, all right? So we'll choose another diagonal that covers a different subset of these squares, right? So I've only covered 3 of the 9 squares in this matrix, right? But I could cover a different 3 by maybe like moving this guy over 1, moving this guy over 1, and then moving this guy over and maybe back around there, all right? Then I get a different set of 3 blocks that again are all independent, so I can parallelize them, right? And then I can shift it again, and now I cover everything, all right? Okay, so they call this a cycle, okay? All right, so after we've covered all the diagonals and we've covered the whole data set, so it's like an epoch in a way, all right? So, so this is the basic idea. So the details then get a little bit more complicated. So within one of these things, so what's happening in parallel? So we've got a yellow machine, a green machine, and a pink machine, okay? So what we're going to do again, so we're doing this in interchangeable blocks, so we have different subsets of the data. So we basically do some, we do something which looks like sequential SGD within this block, okay? And they also randomize how many steps of SGD they do rather than always sweeping through it exactly right. They may go over it more than one, by more than one iteration. And you know, there are lots of experiments in this. It's not clear how important those particular decisions are in this, but that's sort of their process. So within each of these things, we're going to simulate basically doing sequential SGD. So we're going to go through these guys in a random order and maybe go through them a little bit more than once and maybe randomize the step sizes that we're using. Okay, so now we've done one of these diagonals, we're going to move to the next diagonal. All right, so we've gone from here, and then we're going to choose another set of interchangeable blocks, right? And this is one way of doing that, just march everything over to the right. You could march them down instead, or any way you want. The main thing, what matters here is that each one of these blocks has the property that all the rows and all the columns are disjoint from all the other blocks, all right? So the parameters associated with each block are disjoint from the parameters associated with every other block, all right? So we'll take this next diagonal and we'll go through the same process of simulating SGD within that, okay? So they call this stratified stochastic gradient descent, and they call each one of these diagonals a strata. And here's sort of a picture of what they're claiming. So they're claiming basically if you look at the gradient of the loss for this subset of the data and the gradient of the loss from this subset of the data, you can basically add them up. So we can compute them independently and then add them up. Okay. So this is kind of the high-level ideas. There's a bunch of more detail in the lecture. I'm not sure how vital it is to cover this all. Let me move on and mention just a couple of things. So here's the pseudocode. All right. So at some point they changed notation from their paper to the talk. So I'm going from their talk to the paper. So what we used to call V, the target matrix, is now Z. Okay. So what we basically do is we're going to take this. We're going to choose some initial values for these. Okay, and then we're going to construct these blocks. Okay, so that's basically our grouping of the columns and rows into three groups, as I saw before. Except maybe this will be the number of groups will be depend on the number of workers you have. All right, and then we'll basically go through this loop here. We'll pick a step size. We'll pick a strata, which is basically a diagonal. All right, and then in parallel, we're going to run SGD on each of the points in the blocks in that strata, right? And we just repeat that. So that's basically their code. So it makes a difference here because this is not a convex problem. It makes a difference where you start things off, right? So when we talked about perceptron training or we talk about logistic regression, you can start things off at some convenient non-random initial value. Like you could set all the way to 0 and it'll be fine, okay? So here it makes a difference what your initial starting point is. So in particular, if you set these weights to be 0, you can actually show that you're already at sort of a local minimum, right? So, you know, the gradient of W, it's a difference between the target and the prediction times H. Right, and symmetrically, the gradient for H involves a product of W. So if both of those start out at 0, then you'll just stay at 0. So you can't start at 0. So how you initialize sort of matters. Yeah, these are just like some other tricks. So they had some tricks varying step size and so on. And you know, these things all matter because they're sort of trying to beat fairly well-tuned search algorithms. They're trying to beat things like alternating least squares, which is specifically designed for this problem, the mature algorithm. They looked at implementations in Hadoop and also a multi-core approach. So here's some numbers. So this is the iterative stochastic gradient descent. So this is the parameter mixing, which doesn't converge. Okay. This is their distributed stochastic gradient descent. Okay. So this is kind of what they're pointing you out to here, and we can sort of see it is in fact better than the alternating least squares baseline, and these other baselines. Okay. Oh, and I guess this PSGD is, I believe, the parameter mixing algorithm. All right, so that's also converging, but more slowly. This is, basically the same problem with a different set of parameters, so it's a different regularizer. Some of the other ones converge more quickly, but we're still sort of winning here. Yet again, another set of parameters. This is on an even larger synthetic data set, showing that you can get convergence. So one thing we saw before was we saw that as you get more and more, no, wait a second. Yeah. This is basically the same experiment, but they're looking at epochs instead of wall clock time. So this is the number of times you pass over the data instead of wall clock time. So it's sort of giving you the same number of, the same kind of qualitative things. If we look at the number of epochs, then the number ALS is a little bit closer for some of these parameter values. But wall clock time is arguably a better measurement. here's another scalability issue. We can look at varying the number of latent dimensions. So in the pictures I just saw two, which is kind of ridiculous. So here they're looking at the wall clock time per epoch for larger and larger matrices. So if you go from 50 latent dimensions, so that's your vertical, your tall skinny matrix has width 50, right? 50 columns, and you have 50 prototypes. When you go from 50 to 100, then you're basically increasing the size by about of the parameter space by 4, right? You've doubled both W and H. So you should expect to sort of see a linear growth, and that's kind of what you see. It scales okay with rank. And these are the numbers with Hadoop, okay? So this is going from 8 cores to 16 cores, so that decreases the time by half, which is okay. We've doubled the compute time, and we've decreased the time by half. And we double it again, we decrease the time by another half. And then we double again, and now we sort of see we're sort of about as far as we can go. So they claim that at this point, they're sort of running into the startup time to set up a bunch of Hadoop processes. So they're basically saying there's not any further improvement here because now we're sort of, basically sort of being dominated by just the cost of setting up those processes. That's probably something that would be worth looking at a little bit more. And then this is looking at Hadoop and scaling up to larger data sets. So this is going up to from relatively small data sets of 100 million examples up to this very large data set. This is synthetic data of 25 point something billion, right? So what we're seeing here is this is kind of suggesting that they're probably right at some point when the data sets get too small, you're not getting much of a benefit from Hadoop because of startup costs. But you're getting a reasonable scaling factor when you increase the size of the data. Okay, and this is the same experiment with a fixed data size and changing the number of cores. All right. So this is just kind of the wrap up. So matrix factorization is an interesting problem to look at. So there are lots of tasks that can be expressed as matrix factorization. It's also a nice example of a more complex task that you can solve with stochastic gradient descent. So this is a very special case, the fact that we can do this distributed stochastic gradient descent. So we can do it because we can establish this independence. We're looking at different subsets of parameters, and we can break that up and do that independently. There are some other cases where that's possible. You can do some parallelization in neural network settings, for example. Often it's kind of hard to do that in sort of arbitrary models. So that's basically it. So I'm finishing a couple of minutes early today. I will see you guys Thursday. So Thursday, as I said, there is a quiz for today. Thursday, there won't be a quiz. There'll be a review session. It'll probably be less than 80 minutes. I'll stick around and answer questions and stuff like that. Okay? Sure.